G'day boys and girls, welcome back to another episode of McGrathematics for another extension to maths video. We're starting off with a flashback from last week's content. We have a question from the 2021 HSC exam. We are trying to find the angle between these two vectors correct to one decimal place. So not a super challenging question, a good warm up, so pause the video and have a go yourself before I run through my solution. Okay, here we go. So using our angle between two vectors formula from last week, or just from the extension 1 course. Excuse me while I do a gross little cough. Okay, good to go. And edit point. Okay, so for the top, we're going to do the scalar product of the two vectors. So we're going to do 2 times minus 3 plus 0 times 1 plus 4 times 2. On the bottom, we're going to find the magnitude of both vectors and multiply them together. So here we have the dot product on the top, and on the bottom we have the square root of 2 squared plus 0 squared plus 4 squared, which gets us 20, and the square root of 3 squared plus 1 squared plus 2 squared, which gets us 14. Okay, working this out, we end up with 2 over the square root of 280. This is equal to cosine of our angle theta. So to find theta, we'll just do inverse cosine of 2 over root 280, getting us an answer of around 83.1 degrees to one decimal place. All right, so as far as marks in HSC goes, that's pretty much the easiest 3 marks you're gonna get. As long as you know how to use this formula, it's a pretty easy 3%. All right, on to today's lesson, which is looking at geometric proofs. So really applying the content from last week's video into more geometric style questions. Here's our first one. Again, coming to us from the 2021 HSC, we have a multiple choice question. We got 4 cubes placed in a line as shown. As multiple choice, which of the following vectors is equal to vector AB plus vector CQ? Okay, this question becomes a bit more obvious when you start to draw some vectors onto the picture. So instead of drawing AB over here, I'm just going to move it a little bit to the right and draw it between BC. So vector BC is equivalent to vector AB because it is parallel and it has the same length. Now, if we draw a vector from C to Q, we can see that if we want to add AB and then CQ, the resulting vector will be a vector from B to Q. So we're going across 2 units, we're going back 1 unit, and we're going up 1 unit. Let's look at our options. AQ from A to Q is going too far. It's going across and up, but it's going to the right by 3 units instead of 2, so it can't be A. Option B is CP, so from C to P. That's going across 2, back 1, and up 1. So CP is what we need. Vector CP is equivalent to vector BQ, which is AB plus CQ. So option B is the one we are going for. Well done if you thought the same thing. All right, on to example 2. We have a cube shown in the bottom right-hand corner. With the vertex B at the origin, and we have side lengths of 3 units. So our point A is 3 on the X, 0 on the Y, 0 on the Z. Okay, question A is calculate the magnitude of the vector from A to G. All right, so to do that, first thing we should do is find the vector from A to G. To do that, we need the coordinate of the point G. So we can see that G is 3 on the Y-axis and then 3 on the Z-axis. But because it's on the ZY plane, it means its X value is 0. So our coordinate for G is 0 on the X, 3 on the Y, and 3 on the Z. Now to find vector AG, we'll of course do point G, take away point A. So we'll do 0, 3, 3, take away 3, 0, 0. So we end up with minus 3, 3, 3. Now we'll find the magnitude of that vector by doing the square root of the sum of the squared components. So we'll do the square root of 3 squared plus 3 squared plus 3 squared. That works out to be 27, which simplifies to 3 root 3. So there is the magnitude of the vector from A to G. For part B, we are going to find the acute angle between the diagonals AG and BH. So very similar to what we did in the flashback question. First thing we need, we've already got AG. We just did that in part A. We just need to find the vector BH. So from B here up to H, which is 3 on the X, 3 on the Y, and 3 on the Z. Now, because BH is a vector that's starting from the origin, that means the vector BH will just correspond to the coordinate H, which is 3, 3, 3. Okay, imagine we're just doing 3, 3, 3, take away 0, 0, 0. So we're going to get AG from before, and we'll have BH as our vector from the origin to H. All right, we have our two vectors. Now we're going to find the angle between them using our familiar formula. So we'll do the scalar product on the top. So we have 3 times minus 3 plus 3 times 3 plus 3 times 3. Okay, on the bottom we have the magnitude of AG, which we found in part A to be 3 root 3. And now because this is a cube, all of its diagonals are going to be the same length. So the length of BH will also be 3 root 3, which we could very easily show using the formula. But anyway, here is our expression for cos theta. Works out to be 1 over 3, which means our acute angle theta is going to be inverse cos of 1/3, which works out to be around 70.5 degrees. Okay, beautiful. On to example 3. Oh, I love this one. All right, first up, a very useful result in both extension 1 and extension 2 is that the dot product of a vector with itself is equal to the magnitude of that vector squared. We are going to use this fact because it's going to be very useful for a couple of proofs today. We're in fact going to use it to prove Pythagoras' theorem using vectors. All right, starting off with part A, a very simple proof. We are just going to take a vector, let's call it just AB, A on the X and B on the Y. And we are going to do the dot product of that vector with itself. So we'll be doing A times A plus B times B. Now we have A squared plus B squared. If we take the square root of this and square it, we haven't really changed the value of the right-hand side, but now the right-hand side looks like the magnitude of the vector squared. So it equals the right-hand side as required, so we chuck up a QED. Okay, quick little proof that the dot product of a vector with itself is the squared magnitude. All right, let's apply that fact to hopefully prove that in a right angle triangle, A squared plus B squared is equal to C squared using vectors. So we're going to start off this blue vector, I'm going to call it A, and this green one will be B. We're going to say these vectors are orthogonal, aka perpendicular, so there's a 90-degree angle here. Now the red vector is of course going to be vector A plus vector B. Now what we're going to try and show is that the length of this vector squared plus the length of this vector squared is equal to the length of this vector squared. So let's try and prove it. Let's start off with the magnitude, so the length of vector A plus B squared. Okay, imagine like in Pythagoras, this is just C squared. Using our result from part A, we can write the magnitude squared as the dot product of the vector with itself. So A plus B, dot product A plus B. Now we're going to expand these two brackets by essentially doing a binomial FOIL expansion. So we're going to have A dot A, we'll have A dot B and then B dot A in the middle, which we can group together as just two lots of A dot B. And on the end, we have B dot B. All right, cool. Now, a couple things we can do here. Number one, we know that vector A and vector B by definition are perpendicular, and perpendicular vectors, when you do the dot product, you get a result of 0. Okay, so in our expression here, A dot B is equal to 0. And we can write A dot A using our result from part A as the magnitude of A squared, and we can write B dot B as the magnitude of B squared. So using this fact and using this fact up here, we can write our line as magnitude of A squared plus magnitude of B squared. And then what we've just done is we've shown that Pythagoras' theorem holds true because A squared plus B squared is equal to C squared, where A, B, and C are the three lengths of this right angle triangle. Hallelujah, Pythagoras still works. Good to know. All right, on to example 4. Another cool one. We have three coordinates in the X, Y, Z sphere, and we are trying to show that they are collinear. If you haven't heard this word before, collinear means that the points lie on a straight line. What that means is if you drew a straight line between the points A and B and you kept that line going, it would in fact go through C as well. And my computer's being a little frozen. No, it's all right. Okay, cool. So the easiest way to do that for this question is we are going to find the vector between A and B. We're going to find an expression for that. Then we'll find an expression for the vector from B to C. And here's the trick. If we can show that the vector from A to B is parallel to the vector from B to C, we've got two parallel vectors that are going through the same point, which is B. So if you picture that in your head, the only way that can happen is if the two vectors are joined together, forming a straight line. Okay, that's our approach here. Show that vector AB is parallel to vector BC with B as a common point. Let's see if it works. First of all, we'll find vector AB by doing point B take away point A. So we have 2 minus 4, 5, take away 1 minus 1, 3. That gets us 1, minus 3, and 2. Okay, there's our vector from A to B. Now let's have a look at vector from B to C by doing point C, take away point B. So we have 5 minus 13 and 11, take away 2 minus 4, 5. That gets us the vector 3 minus 9 and 6. All right, now if we have a look at this and have a look at this, what you're probably noticing is that vector vector BC is just vector AB multiplied by 3. So we can factor the 3 out of vector BC. And here we are showing that vector BC is a scalar multiple of vector AB. That by definition means that the two vectors are parallel. Okay? So we say since the two vectors are parallel and they have a common point of B, the 3 coordinates must form a straight line. Okay? That's just straight up logic. That's enough for our marker to be like, this person knows what they're talking about. Full marks. On to the next question. Okay, another really cool one. Example 5, we have a point B sitting on the arc of a semicircle with a diameter of AC. Using vectors, we are going to show that ABC is a right angle. So it's a fact of circle geometry that when you draw a triangle inside a semicircle, that triangle will always be right angled. We are going to prove that fact by using vector results, or we're going to try to at least. Okay, some things to note is that A and B and C are all radii of the semicircle, and that A and C are in opposite directions. Okay, so our approach for this one is we are going to find the vector from B to A, so we'll find vector BA, then we'll find vector BC, and we're going to try and show that those two vectors are perpendicular. Okay, easiest way to try and show that two things are perpendicular in terms of vectors is to show that they have a dot product equal to 0. That's what perpendicular means algebraically. Okay, so we're going to do the vector BA scalar product with vector BC. Of course, we know the way to get the vector from B to A is you do A take away B, and BC is C take away B. Now, if we expand the right-hand side once again using a binomial expansion, we end up with A dot C, take away A dot B, take away B dot C, and then plus B dot B. All right, now a few facts we can use here is that, like I said, A and C are both radii, so they are the same vector, just in opposite directions. So what we can really say is that vector C is equal to vector A multiplied by -1. So we can take our expression that we just expanded and we can replace all of our C's with negative A's and see what happens. So at the front, this A dot C is going to turn into a negative A dot A. In the middle, this negative B dot C will turn into a positive B dot A. So it'll look like this. Oh, I got an email. All right. Now this is cool because in the middle, we have negative A dot B plus B dot A. These two things are the same but opposite in sign, so they are going to cancel each other out. Okay, we can also use the fact that A dotted with itself and B dotted with itself from the previous example is equal to the magnitude of the vector squared. So we can change our expression here. The middle terms cancel out, and we can write this as minus magnitude of A squared plus B squared. Okay, now the cool fact we can use is that because A and B are both radii of the semicircle, they have the same length, which means that the magnitude of A is actually equal to the magnitude of B. So these two things are again the same in size, but opposite in sign, which means these two are going to cancel out and leave us with equal to 0. What does that mean? It means that the dot product of BA and BC is equal to 0, which means that these two vectors must be perpendicular, which means we have a right angle inside our semicircle. So there we go, we have proven it. Wasn't that fun? I thought that was fun. All right, on to example 6. We have a rhombus OABC with OA being equal to MI, and then vector from O to C is equal to 1, 1, 1. 1 on the X, 1 on the Y, 1 on the Z. All right, cool. First part of the question is find the value of M. All right, so it's important that the question told us that OABC is a rhombus because it tells us that we know that all the 4 side lengths are the same because it's a rhombus. It's just a square leaning over a little bit. All right, that tells us that if we find the magnitude of vector OC, that should be equivalent to the magnitude of vector OA. And we can use that fact to figure out what the value of m is, because m is just a real number. So there's our approach for question A. We're going to say that the length of OA is equal to the length of OC. So the magnitude of OC is the square root of 1 plus 1 plus 1. And on the left, we have the square root of m squared plus 0 squared plus 0 squared. Left-hand side just works out to be the square root of m squared, which is just equivalent to m. And on the right, we have the square root of 3. So therefore, the value of m must be the square root of 3. All right, groovy. Now, part B, show that the diagonals of OABC are perpendicular. Okay, very similar to approach to the last question. What we're going to do is set up two vectors and show that if we took the dot product of those two vectors, we would get a result of 0. Okay, whenever you're asked to show perpendicular, you're probably going to be showing that the dot product is equal to 0. So first thing we need is our two diagonals. We need to find the vector from O to B, and we need to find the vector from A to C. All right, so to find OB, we can do that pretty easily by doing vector OA plus vector OC. So just adding the two sides of the rhombus will get us the diagonal. Now we know that the value of m is root 3. Here is vector OA, and here is vector OC. This gives us OB, the first diagonal, being root 3 plus 1 on the x, 1 on the y, 1 on the z. Okay, now we'll find the vector from this diagonal here, from A to C. We can do that, or we can do CA, same thing. So vector CA will do point A, take away point C. So A again is root 3, 0, 0, and C is still 1, 1, 1. This gives us the vector root 3 minus 1, minus 1, minus 1. Now, all we need to do to finish off is to show that these two vectors have a scalar product of 0, and that will be enough proof to show that they are perpendicular. So we'll do the dot product. If we multiply the top ones, we do the difference of two squares. So we have root 3 squared, take away 1 squared. So we have 3, take away 1. Then we have plus 1 times negative 1, and then plus 1 times negative 1. This conveniently works out to be 2, take away 1, take away 1. So we get an answer of 0. Therefore, the two diagonals are perpendicular because they have a 0 dot product. And that's the question. The diagonals are perpendicular. Okay, onto the... Oh, mic fell over. Onto the last one, I think. Example 7. All right, this is an example that is designed to look very confusing, but it's actually kind of simple once you read it a few times. We have a trapezium, OABD, in which OA is vector A and OB is vector B. Okay, OC is parallel to AB. Good to know. And the ratio of DC to CB is 1 to 2. Okay, so whatever this length is here from CB, DC is half of that. Okay, using vectors, express the vector from D to A in terms of A and B. Let's have a look at the vector from D to A just here. All right, we need to try and express this vector in terms of vector A and vector B. There's a few ways we can go about doing this. The way that jumped out to me first is I'm going to express dA as the sum of this vector from D to B plus the vector from B to A, okay? These two blue vectors summed together will give me the red vector from D to A. Now, what's an expression for the bottom vector in terms of A? Well, CB is the same vector as OA, so they're parallel. So DC, so this part here is A. Now this part here from D to C is just an extra half of A. So if this one on the top is equal to one whole part of A, the blue one from B to D is going to be 1.5 lots of A, which we can write as 3 over 2A. Now for the one on the right, we can have the vector from B to A. We can just do this as vector A, take away vector B. Okay, that's a useful formula. From B to A is A minus B. So there we have the one on the bottom. So dB is 1.5 lots of vector A, and from B to A is just A minus B. If we get rid of these brackets, we have 1.5 lots of A plus 1 lot of A, so we get 5 over 2A, take away B, and there is your final answer. Like I said, if you know what you're doing, you can get through it pretty quickly just by building triangles inside of your trapezium. Okay, and to finish off today, here is a challenge question for those who like to push themselves a little bit further. This is from the 2021 HSC, and it spans from bands 4 to 5, so it's a pretty challenging question in my opinion. For part I, we're trying to show that HA plus HB plus HC plus HD is equal to 0. That's not too bad. And then parts 2 and 3, in my opinion, are very tricky and require a bit of thought. So by all means, have a go at this. My class will be doing this next week back in class. If you want a hint, let me throw a comment down below and I'll give you some hints, or you can look up the solution for the 2021 HSC and see if that makes sense to you. Good luck. Godspeed. All right, that's it for today. Thank you for watching. Here are some recommended exercises for my class or whoever else, and hopefully catch you in the next video. Cheers for watching.